In recent days, growing public curiosity has focused on what some have described as an unusual silence in official communications following the close Mars flyby of the interstellar object designated 3I/Atlas on October 3, 2025. Multiple fans and readers reached out with questions about why there appeared to be a lack of immediate images, spectra, or press releases from the many Mars-orbiting spacecraft that were well-positioned to observe the object during its passage through the inner solar system. Given the unprecedented opportunity to study an interstellar visitor at relatively close range, expectations were understandably high. However, the absence of rapid public updates has been interpreted by some as evidence of deliberate suppression or secrecy, rather than as a consequence of more mundane institutional and scientific realities. From a technical standpoint, there is no shortage of instruments that could, in principle, have observed 3I/Atlas during its encounter with Mars. NASA's Mars Reconnaissance Orbiter carries the High-Resolution Imaging Experiment, HiRISE, capable of resolving meter-scale features on the Martian surface and of conducting targeted observations of passing objects when geometry and operational constraints permit. NASA's MAVEN spacecraft includes the Imaging Ultraviolet Spectrograph, IUVS, which can probe tenuous gases and ultraviolet emissions that might arise if an object were actively outgassing. On the European side, ESA's Mars Express hosts the High-Resolution Stereo Camera, HRSC, along with a suite of spectrometers such as Omega and Spicum, designed to analyze mineralogical and atmospheric signatures. The ExoMars Trace Gas Orbiter, TGO, adds further observational power through CASIS imaging and spectrometers like ISCM and NOMAD, optimized for infrared and trace gas detection. Beyond NASA and ESA, China's Tianwen, one mission includes the Moderate Resolution Imaging Camera MORIC, and the United Arab Emirates HOPE Orbiter carries the Emirates Exploration Imager EXI, as well as the EMIRS and EMU spectrometers, extending coverage into the infrared and ultraviolet. In other words, the observational infrastructure exists, and it is both international and highly capable. The key misunderstanding lies not in the availability of instruments, but in how data are acquired, processed, validated, and released. Spacecraft operations are governed by carefully planned timelines, finite data bandwidth, and competing scientific priorities. Observing a fast-moving interstellar object is not as simple as pointing a camera and pressing a button. It requires advanced planning, precise ephemerides, onboard resource allocation, and coordination among mission teams. Even after data are successfully acquired, they must be downlinked to Earth, calibrated, checked for artifacts, and interpreted by specialists. Large research teams often take days or weeks to ensure that what they are seeing is real, properly understood, and placed into scientific context. Premature release of unvetted data risks misinterpretation, sensationalism, and, ironically, further erosion of public trust. Compounding these routine delays are external factors that have nothing to do with science itself. At the time in question, NASA has been affected by AUS, government shutdown, a recurring political event that disrupts agency operations, delays data processing, and places many civil servants and contractors on furlough. When key personnel are unavailable, workflows slow dramatically. This is not evidence of a cover-up nor of extraordinary discovery, but rather of the fragility of large institutions operating under political constraints. As I explained to those who asked, long delays in public reporting are far more often a signature of terrestrial human bureaucracy and inefficiency than of extraterrestrial intelligence. During this period of limited official communication, another line of questioning emerged, this time focused on orbital dynamics rather than institutional behavior. Some readers asked about the significance of the approach angle of 3I/Atlas relative to the ecliptic plane, the plane defined by Earth's orbit around the Sun. In a recent essay, I noted that the trajectory of 3I/Atlas is aligned with the ecliptic plane to within about 489 degrees, and that such close alignment is statistically rare if interstellar objects arrive from random directions. Estimates suggest that the probability of such an alignment by chance is on the order of a fraction of a percent. This led to speculation about whether interstellar objects originating in the Milky Way disk might naturally be biased toward small inclinations relative to the ecliptic. To address this, it is essential to distinguish between different reference planes in astronomy and to understand their orientations. The ecliptic plane is defined by the angular momentum of the solar system's planetary orbits, while the plane of the Milky Way disk is defined by the collective angular momentum of stars orbiting the galactic center. These two planes are not aligned. In fact, the ecliptic plane is tilted by roughly 60 degrees relative to the galactic midplane. This misalignment is substantial and immediately undermines the idea that objects coming from the galactic disk would preferentially approach along the ecliptic. If anything, the large angle between these planes makes close alignment with the ecliptic less likely, not more. The concept of alignment probability can be framed quantitatively using angular momentum vectors. Each plane corresponds to a direction in space, represented by a vector perpendicular to that plane. The probability that two such vectors are aligned within a small angle scales with a solid angle defined by that angular separation. For small angles, the solid angle scales approximately as the square of the angle itself. As a result, the likelihood that a randomly oriented trajectory would align within just a few degrees of the ecliptic is intrinsically small. When a reference plane of origin, the Milky Way disk, is itself tilted by about 60 degrees relative to the ecliptic, the odds of a near coincidence like that seen for 3I/Atlas drop to well below 1%. Galactic dynamics further reinforce this conclusion. The stars in the Milky Way disk do not move on perfectly circular, coplanar orbits. In addition to their average rotation around the galactic center, they possess random velocities amounting to roughly 10% of their rotational speed. These random motions cause stars to oscillate above and below the galactic plane in what is known as epicyclic motion, driven by the restoring gravitational force of the disk. Locally, the velocity dispersion of stars is comparable in all three spatial directions to within a factor of about 2. This means that stellar motions are not strongly confined to the plane, and neither are the motions of smaller bodies ejected from planetary systems. Interstellar objects are expected to inherit the kinematic properties of their parent systems. When planetesimals are scattered out of planetary systems by gravitational interactions, they carry with them the velocity distribution of the stars they orbit. As a population, such objects should therefore approach other planetary systems, including our own, from nearly isotropic directions. This expectation has been supported by recent theoretical studies, which show that there is no strong directional bias favoring the ecliptic or any other specific plane. The solar system should be bombarded by interstellar objects arriving from all over the sky. Observational evidence from previously detected interstellar visitors is consistent with this picture. The first known interstellar object, 1I/Oumuamua, entered the solar system on a highly inclined trajectory, with an inclination of about 123 degrees relative to the ecliptic plane, effectively coming in from a direction opposite to the planetary orbital motion. The second confirmed interstellar comet, 2I/Borisov, arrived with an inclination of roughly 44 degrees. Neither of these objects showed any preference for the ecliptic plane, and both were well within the range expected from an isotropic distribution of arrival directions. Against this backdrop, the trajectory of 3I/Atlas stands out. An inclination of just under 5 degrees is anomalously small when compared to both theoretical expectations and the limited but informative observational sample. This does not automatically imply anything artificial or extraordinary, but it does warrant careful statistical and dynamical analysis. Rare events do occur